All right, this will be our last video for the Chapter 18, for the Chapter 18 series of videos focusing on acid-base chemistry. And this last one, we're going to look at one more new definition of acids and bases, and it's going to be the one that is used in organic and inorganic chemistry the most. So many of you in 1520 are going to move on to organic. And this is the acid-base definition that applies most often there, right? So we're kind of digging down to more specific, right? So less specific at the Arrhenius end and more specific in terms of what is going on and what we define as an acid and base on the Lewis side of things. So first, let's recap what an Arrhenius acid and base are and what a Bronsted-Lowry acid and base are. So an Arrhenius acid is any substance that produces H3O plus in water, and an Arrhenius base is a substance that produces OH minus in water. Done. That's it. Very, very basic definition. That could cover a lot of different things. Okay. So now let's look at the Bronsted-Lowry definition. So for an acid, this is a proton, which is H plus, acceptor. Donor. Oops, already screwing up here. Donor. And so it must have covalently bound H atoms in its structure to be a Bronsted-Lowry acid. Move this down a little bit here. Okay. On the base side of things, for something to be a Bronsted-Lowry base, it must be a proton acceptor. And so to be able to accept H plus, your molecule must have lone electron pairs available. Okay. The idea being, let me show you here. Okay, let's say we have H here and it's bound to A. Thusly, that red line represents our 2 electrons. Then we have a base here with our 2 electrons. And so what can happen here is the 2 electrons here can grab that H plus, causing these 2 electrons to become a lone pair. And so we end up with A minus and HB plus. And so in HA, the 2 electrons that were in the bond with the H now become a lone pair, and the 2 electrons on the base that were a lone electron pair now become the bond to the H that it is captured. If you remember, these types of reactions are proton transfer reactions. Okay? So you need an acid and a base, and they swap an H plus between them. Let's look at the Lewis acid-base definition. So if you think about Lewis, right, the associated word should be dot structure. And that should tell us this has to do with electrons, whereas Bronsted-Lowry had to do with protons. So in the Lewis definition, a Lewis acid is an acid that is an electron acceptor, which means that a Lewis base is an electron donor. So their roles have swapped, but what they're accepting and donating is different. So to be an electron acceptor, this molecule must have an empty molecular orbital to accept a lone pair into, and to be an electron donor, you must have a lone electron pair. Now, the way Lewis acid-base chemistry works is we would have our A with our empty molecular orbital, and it reacts with our B, which has a lone pair. I'm going to draw them as so this is our lone electron pair. And I want you to think of Legos when you think of Lewis acids and bases. And I say that because in Legos, you have the outie part that snaps into, every Lego also has on the back end an innie part. And so Legos stack outie to innie. So when a Lewis acid interacts with a Lewis base, they form something called a Lewis acid base adduct. So rather than swapping anything, they click together. Pair of electrons in an orbital into an empty molecular orbital. And so if we go back and look at Bronsted-Lowry, H plus is a Lewis acid. And the things that want to interact with it are both Lewis bases. Let me make this, make this red. So really, Bronsted-Lowry proton transfers are actually one Lewis acid base adduct splitting, freeing up the Lewis acid H plus to form a new Lewis acid base adduct with the base. So we've been looking at Lewis acid base chemistry all along. This is what I mean by it's a deeper and more specific definition of acids and bases. Okay? So what kinds of things have empty MOs? And basically, when we say empty MOs, we mean electron deficient. So what kind of things are Lewis acids? Well, H plus, metal ions, boron compounds, aluminum. So when I say metal ions, that could be like a sodium, or that could be like a sodium. Actually, it's more transition metals that we see this with, but transition metal ions. These are all Lewis acids. They have empty orbitals and are electron deficient. If you'll remember, boron and aluminum don't form an octet. They want 6 valence electrons, so they've got to spot a hole, if you will, to put 2 more electrons into. So they will want to interact with a Lewis base. Now, what's a Lewis base? Well, remember the criteria for a Lewis base is a lone electron pair. Well, Lewis bases are any molecule with lone electron pairs in its structure can act as a Lewis base. Okay? And so let's look at some examples of this. Let's say we have H plus and OH minus, and they're going to come together to form H2O. We're looking for the Lewis acid and the Lewis base, and indeed, this is what we have here. This is going to act as the Lewis base, and this is going to act as Lewis acid. How do we know that? Well, this is pretty easy. H plus doesn't have any electrons, so it cannot meet the definition of a Lewis base, and OH minus. And so what normally helps with these, by the way, is you want to draw the Lewis structure for things. Well, there's what makes it a Lewis base. Okay, let's look at another one. Let's say we have Cl minus plus BCl3, and its adduct form is BCl4 minus. So let's look at this one. Which one's the Lewis acid and which one's the Lewis base? Well, again, let's draw a structure here. Okay, there's the Lewis structure of BCl3. Note 6 valence electrons, as we learned in 1510. And then Cl minus is just this. Now, you may initially think, well, the BCl3 has lone pairs. That doesn't automatically mean it's going to behave like a Bronsted, like a Lewis base. This means that this is going to be a Lewis acid because we're electron deficient. So that means our Lewis base then is our chloride ion here. So you're looking for the electron deficient species, that's the Lewis acid, and then the electron rich, or the thing that has lone electron pairs, that's your Lewis base. All right. And that concludes the material for chapter 18.